Good day everyone, my name is Cheryl B. Dalida from BSED Science 2A and today we are going to discuss the chapter 9 entitled The Sun. Learning objectives. First is analyze the structure of the sun and describe the different features of the sun. Next is understand the sun mechanism and lastly explain the process of the sun. But before that, let me ask you something. What do you think is the brightest star in the Earth's sky? If your answer is sun, then you'll get the right answer. And the sun is the sphere of hot gas made up of 99% of the solar system mass. Its radius is about 696,000 kilometers or equal to the 100 Earth radii. Its mass has a 300 times compared to Earth, and it is made up of 70% hydrogen, 28% helium, and 2% of carbon and nitrogen. Next is the history of the sun. The sun was born about 4.5 billion years ago, and many scientists think the sun and the rest of the solar system formed from a giant rotating cloud of gas and thus known as the solar nebula. As the nebula collapsed because of its gravity, it spun faster and flattened into a disk. Most of the material was pulled toward the center to form the sun. And now, let us discuss the regions of the suns. First one is the core, second one is the radiative zone, next one is the convection zone, transition zone, photosphere, chromosphere, and the corona. The first layer is core. The core of the sun is considered to extend from the center to about 0.2 to 0.25 of solar radius. It is the hottest part of the sun and of the solar system. Temperature at the sun's core is around 15 million degrees Celsius or 28 million degrees Fahrenheit, which is almost 3,000 times higher than at the surface. The core is 10 times as dense as gold or lead, and the pressure is 340 billion times the atmospheric pressure on Earth's surface. It is where the thermonuclear fusion takes place. Thermonuclear fusion is the process where the temperature inside the core is combined with the sun's gravity and they fuse together with hydrogen molecules and then it will create a helium. This thermonuclear fusion releases an enormous amount of energy in the form of radiation, electricity, solar wind, heat, and light that we are experiencing here in Earth.
Devastating Category 5 hurricane can top over 150 miles per hour, or 241 kilometers per hour. Now imagine another kind of wind with an average speed of 0.87 million miles per hour, or 1.4 million kilometers per hour. Welcome to the wind that begins in our sun and doesn't stop until after it reaches the edge of the heliosphere, the solar wind. The corona is the sun's inner atmosphere, the brightness that can be seen surrounding an eclipsed sun, and home to the continually expanding solar wind. Right now, the Parker Solar Probe, a NASA mission launched in 2018, is orbiting the sun and will get as close as 3.83 million miles, or 6.16 million kilometers, of the sun's surface. Parker is gathering new data about the solar particles and magnetic fields that comprise the solar wind. More specifically, two of its main goals are to examine the energy that heats the corona and speeds up the solar wind, and determine the structure of the wind's magnetic fields. While many theories describe the solar wind's history, this is what we do know. The solar wind impacting Earth's magnetosphere is responsible for triggering those majestic auroras, typically seen at locations close to our north and south poles. In some cases, it can also set off space weather storms that disrupt everything from our satellites in space, to ship communications on our oceans, to power grids on land. Nikki Fox is the Division Director for Heliophysics at NASA headquarters. She explains in more detail how the solar wind disrupts our magnetosphere. As the wind flows toward Earth, it carries with it the sun's magnetic field. It moves very fast, then smacks right into Earth's magnetic field. The blow causes a shock to our magnetic protection, which can result in turbulence. NASA also has another reason to study the solar wind and its properties. The solar wind is part of a larger space weather system that can affect astronauts and technology. As Fox notes, we not only have to ensure our astronauts are protected from the harmful effects of radiation, we have to protect our equipment too. So we've already found aluminum to be a good shield to protect our crafts from many energetic particles. But there are also faster particles that travel at 80% of the speed of light, which can cause havoc with parts of a spacecraft. They can smash into and damage solar panels, disrupt electronics, or affect electric currents that flow along power grids. So we're currently conducting tests with small pieces of technology to study how well they can survive in intense radiation areas. Knowing more about the effects of the solar wind is not only important to those of us who live on Earth, it will be critical to know how to mitigate its effects once our astronauts travel back to the moon and beyond for extended periods of time.
Next is the radiative zone. The radiative zone is where the site where energy transport occurs, meaning the energy produced from the core is carried outward here. This zone can be characterized as the place where the photons bounce around, facilitating the ability for energy to be transported to the outer surface of the sun. The temperature at the radiation zone ranges from 2 to 7 million degrees Celsius. This zone is little cooler than the core. It is highly ionized, very dense gas under constant bombardment by the gamma rays from the core. According to NASA, a single photon can take 100,000 years to travel from the core to the radiative zone and to the photosphere. Next layer is what we call the convective zone. The convective zone is the outermost layer of the interior of the sun. It extends from a depth of 200,000 kilometers up to the visible surface of the sun. Energy is transported by convection in this region. The surface of the convection zone is where light and heat is created because photons are converted into heat and carried out by convective currents. Take note that the movement of convective current is like a boiling water. Next is the photosphere zone. The photosphere is marked by bright, bubbling granules of plasma and darker, cooler sunspots, which emerge when the sun's magnetic field breaks through the surface. Sunspots appear to move across the sun's disk. Observing this motion led astronomers to realize that the sun rotates on its axis. Remember that the sunspots form as a result of the process in the sun's interior. It is also studied that energy created 1,000 years ago from the core was finally escaped into space. After 8 minutes, we can now be able to feel the effect of this process by the form of heat and sunlight. Next layer is what we call the chromosphere. It is the lower region of the sun's atmosphere, and its name comes from the Greek root chroma, meaning color, for it appears bright red when viewed during a solar eclipse. It is made up of hydrogen and helium plasma, which is ionized to produce red visible light as seen during eclipse. The chromosphere extends for about 2,000 kilometers above the visible surface of the sun. The chromosphere may play a role in conducting heat from the interior of the sun to its outermost layer, the corona. Next layer is transition zone. The transition zone is a thin and very irregular layer of the sun's atmosphere that separates the hot corona from the much cooler chromosphere. The temperature here rises abruptly from 7,700 to 500,000 degrees Celsius. Researchers still do not understand why the temperature rises so much in this outermost layer of the Sun, which are far from the heat-producing core. It is suspected that the complicated structure of the Sun's magnetic field may provide clues to the dramatic increase in temperature. These ions emit light in the ultraviolet region of the solar spectrum that is only accessible from space. Next layer is what we call the corona. But why is corona so hot? The corona reaches extremely high temperatures. Astronomers have been trying to solve this mystery for a long time. The corona is in the outer layer of the Sun's atmosphere, but it is still 100 times hotter than the Sun's surface. And NASA discovered a very hot material called heat bombs that travels from the Sun into the corona. In the corona, the heat bombs explode and release their energy as heat. Next is the coronal loops and streamers. The surface of the Sun is covered in magnetic fields. This is the force that makes magnetic sticks to metal, like the door of your refrigerator. Its magnetic fields affects charged particles in the corona to form a beautiful features. This includes streamers, loops, and plumes. We can view these features in detail with our telescopes. How does corona cause solar winds? Well, the corona extends far out into space. From it comes the solar wind that travels through our solar system. The corona's temperature causes its particles to move at very high speeds. These speeds are so high that the particles can escape the Sun's gravity. The Sun's corona is usually hidden by the light of the Sun's surface. That makes it difficult to see without using special instruments. However, the corona can be viewed during a total solar eclipse. Take note that corona can only be seen when eclipse happen. And as a conclusion, we can view this table as a reference. First, we have here the core, where the hydrogen and gravity and temperature fuse together to form a helium, or what we called the thermonuclear fusion. This thermonuclear fusion produces a energy in the form of radiation, electricity, and heat. Next one is the radiative zone, which the energy that was created from the core was carried outside here. NASA states that photons came from core takes 100,000 years to travel into this zone. Next is the convection zone. It is where the photons from radiative zone will converted into heat and carried out by convective currents. Next layer is the photosphere zone, which energy that was created 1,000 years ago finally escaped into the space by the form of heat and sunlight. It is also where we can see the sunspots due to the process that takes place in the interior of the Sun. Next is the chromosphere zone. It is where the chromosphere conducts heat from the interior of the Sun to its outermost layer, the corona. Next is the transition zone, where ions emit light in the ultraviolet region of the solar spectrum that is only accessible from space. And lastly, the corona. Corona is covered in magnetic field, and this is the force that makes magnetic sticks to metal, like our door in our refrigerator. I think that is the end of my slide, and I hope you learned something from me. And remember that sun is very important in terms of our living, because it sustains life. Have a great day, everyone. God bless.